Now, in this lecture, we shall be discussing about the practical design of a steel compression member, and we shall be discussing how the software is calculating that so that we can cross-verify the results that we are getting from the manual calculations and can practically understand how the compression members are designed in ETABS. So first of all, we can go to use built-in settings, and we can use the display unit as metric SI. Region is Australia. Steel section database in Australia and New Zealand. Steel design code, obviously that has to be AS4100 2020, and concrete design code that can be AS3600 2018, although we shall be using AS4100 2020 only. So we can left click on OK, and after that we do need to understand that the example that we are having, the length is approximately 5 meters, and the section size name is 310 by 158, with plate thickness having 25 mm. So accordingly, we shall be selecting the materials also and section property also. So you can number of grid line in X we can select it as 2, Y also as 2, spacing of grid that basically doesn't matter. Number of stories we can select it as 1, story height here as 5 meters, and we can left click on OK. So we can close this model explorer that is not of much use to us, and after that we can close this view also, and we can first of all we do need to go to the define material properties. So in here we can select add new material Australia steel, and in here we do need to select grade 350, thickness between 11 and 40 mm, as the thickness of the web is approximately 15.7 and thickness of flange is 25 mm. So we can select this property and left click on OK. And here we can left click on modify show material design property, and the yield stress is approximately 340 MPa, and tensile strength is approximately 480 MPa. So we can left click on OK, and here these are the non-material properties. So we shall be I shall be making a separate course for the non-linear and we can say performance-based design. But in right now we shall be discussing on the theoretical analysis of the compression member in this particular lecture. So after that, we can go to define section properties and frame sections, and left click on import new properties, steel I section, and in here we can select 310 UC 158 and left click on OK. So we can left click on modify show property also to check the thicknesses of the flange and web just for the confirmation. And in here web thickness 15.7 and flange thickness is basically 25 mm, the same that we had discussed here. So you can just left click on show section properties also to see the section properties. So in here we can see that area, gross cross section area, that is approximately 20100 mm square, and or we can say 201 centimeters square. So here also it is approximately 201.30, we can say, centimeters square. Similarly, it has calculated the section modulus also, radius of gyration also, fillet radius also, and all those steel sectional properties. So we can left click on so in here we do need to select this particular option, that is 3679.1 350, thickness between 11 and 40 mm. So we can left click on OK, and then again we can left click on OK. So now we have uh, uh, provided the input of material properties, section properties also. So the good thing is that if we are using the ETABS software, just ensure that all of the options are checked in define tab itself. Material properties is checked, section properties is also checked. After that, we can go to the load patterns, but before that, we can draw the column itself. So we can go to the draw beam, column, and brace, and we can again go to the draw beam, column, and brace option here. So in here, we can select the steel properties as 310 UC 158. So before that, we can just go to the draw and snap options again. Draw and snap options. So in here we can select line ends and midpoint, perpendicular projections, lines and points, and then again we can left click on apply and OK. So in here we can see that now it is snapping onto the grid point A1 base, and we do need to go up to grid point A1 story. So now if we check, go to the select object option, left click, and then again right click. So the height of the member is approximately 5 meters. Assignment is basically 310 UC 158. So we can select the bottom node again, and we can go to the assign, joint, and restraint. We can provide it as fixed also. That is not an issue. And after that, regarding the top node, we can keep the free node as it is. We shall explain the in shortly, but before that, we can go to the define and load patterns. In here, you shall see that we are having dead load and live load also. Considering this as theoretical analysis, I shall keep it as dead load only. And then after that again, by just left click on, sorry, we can say click the escape option on a keyboard, and then again select this node and go to the assign, joint load and force. In here we can select the global Z as -4000, in line with what we had discussed, or we can say studied in our theoretical example in our previous lecture. So we can left click on OK, and in here you can see that now the 4000 kN load has been applied. So in here you can see that FZ is approximately 4000 kN that has been applied to this particular node. So load patterns are okay, load cases are also okay, and then after the load combination, so we can left click on add new combo and then just keep it one as it is and name it as we can say com1, that is combination 1. So as this is theoretical analysis, although for the as per the Australian standard, it should be 1.35 time dead load, but again we are just doing the theoretical analysis considering the 4000 kN, so that we can compare the results that we had calculated in this lecture with what the software is projecting. As you know, it is very important to understand how the software works. It is not that we can put any kind of data without any kind of, we can say, correlation, and then it shall be, we can say, we cannot blindly follow the results. We should understand what we are handling. So that is why it is very important to understand how the software calculates each and every equation, each and every solution. So load combinations are also selected. After that, we can go to the analyze and set active degrees of freedom. So we can go to the XZ plane only, as we are doing the analysis in this particular plane only. So we can left click on OK here. And after that, load combinations are also selected, and then we can just go to the analyze and run analysis option. So we can see that there has been a vertical displacement of 4.8 mm approximately. So the member has, we can say, compressed along the vertical axis. So now we can go to the design, steel frame design, and view revised preference. So in here you can see that by default design code AS4100 2020 has been selected. And after that, we are doing the moment frame, hot roll section is also okay, and then we can left click on OK again. Again, we do need to go to steel frame design and select design combinations. So in here, you can just select the combination one as the strength also, and for the deflection also. That is not an issue. And after that, yeah, so we can left click on start, design, and check. So in here, you can see that it is red in color. So we can just right click here and then see that, it is, the member is not safe. Basically, what is happening is that, the we can say, as per the degrees of freedom that this particular we can say column is having. So this is the column that we are having. We can just right click here and set grid system visibility. It shall switch off the grids. So this is the simple column that we are having. So what we can do is that we can just left click and then again right click, left click on overrides. So in here you can see that the effective length factor KE, the one that has been considered as 1 in this analysis. So in this analysis, basically we had assumed that the total length is, or we can say effective length is 5 meter only, or 5000 itself. So what we need to do is that we need to select it as 1. This also needs to be selected as 1. Effective length factor braced also, this also we can select it as 1. Now this factor, that is KT, KL and KR. So you must have studied in your universities also, or in higher education also. Basically, these are used in the beams also. And beam columns. Beam column is a term that denotes the vertical members on which we are having the moment also. So basically, theoretically, all the columns that we see in our real life building structures, those are beam columns itself. Those are not standalone columns as per the code. So as of now, we can select keep it as 1.4 also. That is, that shall not be impacting our design because we are only having the vertical force. So we can just left click on OK here, and here also one more thing, yield stress that has been selected as 340 MPa. So that is also okay. Now as you do that, as you change the overrides, here you can see that now it is showing the design that is at the station location 0, that is at this particular point. We are having the axial interaction, or we can say axial force utilization as 0.902. Basically what the software do is that it calculates the axial ratio, it calculates the bending major ratio, it calculates the bending minor ratio. As in our case, we are not having any kind of bending moment along the major axis or minor axis. So that is why, it is only showing the axial forces. And in addition to that, we are not having any kind of shear forces also in this particular theoretical analysis. So that is why you can only see the axial utilization here, and you can only see this particular value here. After that, we can left click on details option here. So when we left click on details option, this whole design window comes. As an engineer, you do need to learn how to, read these values. Unless you just want to be a modeler, you are not a modeler, you are an engineer. So you do need to understand the meaning of all of these terms that has been used here. So all of these are design code parameters, that is the phi, which ultimately needs to be multiplied with the final calculated value, that is 0.9 for compression members. So phi c, that is 0.9, and that is understood. And after that, these are the section properties that also we have understood, that is 201 centimeters here of the cross sectional areas. This is basically the Z and I. These are the second moment of area and section modulus. Material property we know 205000, that is the section modulus. Fy is basically 350y. Our steel gate is 350, but as per the thickness is high, so we have to consider 340 Newton per mm square, or 340 MPa is the yield strength. So in this case, you can see that our, we can say, the total load that is coming is 4007.73 kilonewton. Now, that is a little bit different from what we had calculated in the theoretical analysis. Basically, what was happening is that this additional 7.7367 is the self weight of the member, which we had calculated in the dead load itself. So that is why you can see a little bit of higher number here. After that, when we're talking about the basic factors, that is major, minor bending, LTB is lateral torsional buckling, that we shall be discussing in detail in the beam section. So after that, all of these factors has been taken as one. KT, KL and KR, they do not, are not of much importance to us. Now, these are the values that are important to us, that is K, F, KT, alpha B and alpha C. Alpha B, as you know, that it is a hot rolled section. For hot rolled I section, alpha B is 0. And on the basis of that, we can calculate the value of the alpha C. Alpha C is the one that is basically dependent on your lambda. So if we refer to the, the value that we had taken in our design calculation here. So for the, we can say, minor axis, you can see that the value that has been calculated as per the theoretical analysis 0.723. So this is the value that has been taken in our final calculations. So here you can see that it is 0.722. So it is more or less same itself. So that this value is matched. After that, if you're talking about the major flange web, minor flange web, axial flange web, in here it is checking that what is the compactness parameter, whether the section is, we can say, compact or whether it is slender. So here it is saying that it is non-slender. Why? Because this particular ratio, lambda e by lambda ey, is in some particular ratio. this is the maximum, we can say, these are the maximum allowable values that we had already discussed in our theoretical analysis. So moment and capacities, they are not of much importance to us because m star, that is the moment that is coming on your member, that is 0. So that, we won't be spending time on. This is the important one, that is axial capacities. So if we are talking about the axial capacities, basically n star is the value of the axial force that is coming. So that is approximately 4007 kilonewton. That is the axial force that is coming. This is basically the S, N, C, and N, T, and N, O, Z. Now, if we refer to the what we can say as the NT, that is basically the tensile capacity. We are not dealing in any kind of tensile capacity. If we're talking about the NC, this is the value that is of much importance to us. That is 4936.2. If we refer to the value that we have calculated here, design member capacity, section capacity, and compression. So this is basically the value. Here you can see that it is basically 4947. So 4947 against, and our value that we are getting is 4936, which is again multiplied with 0.9. So here this value, so phi c into nc, so that gives us approximately the allowable, we can say, capacity of the compression member, the final value that we shall be using. So to check that final value, what we can do is that we can left click on overrides here, and in here you can see the final compressive capacity is 442.5438. So our value was 4452.3. In here we are getting 4442.5. So there's a difference of, we can say, 10 kilonewton, and obviously that do comes when we are doing the theoretical and manual calculation. We are comparing the theoretical and manual calculations. So I hope the concept is clear to you. That is, you should not just blindly trust the design results by ETABS. You do need to check all of these options here. Only after that you can ensure that whatever the calculations you are doing is correct or in line with the theoretical analysis. So I hope this design example is clear to you, and if required, you can just go through the code again. As I said, all of these calculations are done by the, we can say, software itself, and the code itself has simplified by providing us this particular table. If you are having an RHS section, rectangular hollow section, you shall be having alpha b as -1. So if required, you can just do another example here, and then we can just compare the results. And in that particular example, if you shall be checking the details, in that case, this particular value, that is alpha b, it shall not be 0, it shall be -1 if we are using the rectangular hollow section, and this shall not be, also will not be hot rolled, this shall be rectangular hollow section. So that is how you can check the design results in ETABS and compare that with the help of the manual calculations.